Welcome to Module 10, System Protection. In this module, we're going to talk about the different elements and equipment and components and designs and schemes that are used to protect the electric power system from things like lightning strikes and power faults and high voltage equipment failures and those types of things. The protection system is something that is very detailed, very extensive. There are several, thousands of electronic relays and electromechanical relays and protection schemes that keep our system intact. When something goes wrong, the protective relays are usually there to trip circuit breakers or make changes faster than system control operators can do anything. So in this particular module, what we're going to cover are, number one, explain the differences between system protection and personal protection. Number two, we're going to discuss the fundamentals of solid state and electromechanical protective relays. We're going to describe the various protective relay schemes in use today. And we're going to describe how to synchronize a generator onto a power grid. Okay, so when we start with the two different types of protection, system protection versus personal protection, the main difference is system protection involves all the electromechanical and solid state protective relays and schemes that are used to trip breakers and do all those kinds of things automatically. Personal protection has to do with the rubber goods and conductive grounding and different personal grounds and all these different things that we're going to talk about later in safety, where personal protection is something that construction workers or maintenance workers or line crews use to protect themselves personally when they're working in high voltage environments. So the difference is system protection, the relays, the electronics and what have you, the system protection is a completely different type of protection, and that's what we're going to focus on here is system protection. And I want to point out something, that system protection is not designed or does not have, it's not designed necessarily to protect human life. In other words, it's protecting the system. We don't set relays or whatever just to make sure that if someone actually touched a power line, they're going to survive it. Protection, system protection has to do with conditions on the system that, if abnormal, the protective relays will operate. Whereas personal protection is designed for human safety and being able to work in high voltage environments. So there's a difference there, and I just wanted to make that clear to you. So we're going to talk about system protection. Okay, there are two types of protective relays in general. There's the microprocessor-based and the electromechanical. Now the microprocessor-based is more of a newer type relay scheme or relay equipment versus the older type electromechanical. The electromechanical was in use for many, many years, and when we talk about electromechanical, there's coils in there creating magnetic fields which are turning disks, and when a disk turns, the contacts come together and says, okay, I had enough magnetic field to turn my disk so far against certain type of tension on a spring, but the contact's still connected, and that connection of those contacts tripped a circuit breaker. Now on the electronic or microprocessor based, the CTs and PTs, that analog information, the low voltage, low current that's scaled down from the real system, okay, is digitized and put into a microprocessor base, and then you have voltage comparators and you have all kinds of protective schemes involved when the sampling and the certain thresholds and conditions are met electronically, then switches are closed or contacts are made up, and then that's what's controlling the circuit breakers. So keep in mind that circuit breakers used in high voltage equipment are pretty much dependent on protective relays telling them to trip. You can trip breakers with supervisory control through SCADA. You can manually trip and open, close breakers manually. But when it comes to automatic system protection, it's these relays that say, okay, I have a overcurrent condition, or out there on the line at a certain distance I'm having a fault and it's a current that's much greater than normal. So those settings are pre-programmed into the microprocessor, or springs and tension are set in an electromechanical relay that say, okay, this is an abnormal condition, trip the breaker I'm assigned to. And then you have relays that are looking for over and under voltage conditions, or bus and transformer differentials. When you have a differential, that means, for example, on a transformer, if the power going into the transformer is not equal to the power coming out, there's an abnormal condition. There must be either an internal fault or an external fault on the transformer, because not all the power is getting out. So you end up with a condition of differential, and the circuit breakers surrounding the transformer become tripped open and de-energize the transformer. Okay, then we have like bus differential, where you have the current going into a bus from a transformer, let's say a single transformer in this case. Then that current going into the bus must equal all the currents going out of the bus on all the different feeders or transmission lines. If there's a differential between all the currents going out into the feeders or out into the transmission lines, not matching what's coming out of the transformer, then there's a bus differential problem. And maybe there's a bird in a bus, or there's some kind of condition in a bus that says, okay, trip the breakers and de-energize everything. And usually that means someone has to go out to the substation and figure out, is it an internal fault or an external fault, and then you go from there. Then we talk about other types of relays. There's under frequency. If the frequency drops, let's shed load. Or there's several. There's add a step. There's so many different schemes. It's amazing what's out there. We're just going to give a little overview so you get a fundamental idea what system protection and protective relays are all about. Okay, let's start with a simple one-line diagram. You're going to get very familiar with these, especially when you use the simulator. But here we take a simple one-line diagram. This shows, a fuse and a lightning arrestor connected to a ground where the lightning arrestor is grounded. And when we talk about a one-line diagram, it's really representing the three phases, but why draw all three? So we're looking at a single one line that kind of represents three phases. And then you see there's a disconnect switch like we talked about in the earlier module, a transformer that's hooked up delta on the high side and grounded Y on a low side. And because there's an arrow through it, it's a tap changing transformer, an LTC, load tap changing transformer, like it has a regulator built in. Then you see a circuit breaker, and those little circles, the 50, the 51, the 81, and the 79, those little circles represent what type of protective relays are associated with that breaker. So when you look at that little table on the right, a 50 is an instantaneous overcurrent. That means there must have been a fault close into the substation that had an instantaneous overcurrent short circuit condition. That breaker is going to trip. And then it has a 51 relay, which is an AC time overcurrent relay. And that just means that, when the fault is there for a period of time, then it's going to trip. And there's a time delay to allow downstream fuses to blow first. There's an automatic reclosing relay, like we talked earlier about reclosers. If there's a lightning strike, the instantaneous overcurrent, most likely to trip, and then the 79 reclosing relay will reclose the breaker after a certain period of delay. And then there's a frequency relay, the 81. That's where we have load shed. If the frequency drops below a certain set point, then it's going to trip that breaker. And these are the relay schemes. There are many more out there. This is typical of distribution. But when you get into transmission and you get into loop conditions and network and transfer trip and so many different other schemes, it gets very elaborate, very involved. But for now, we're going to talk about an overview of what system protection is all about. Okay, in this slide, an important concept here to recognize, and that is an inverse time relationship. With protective relays, if the current in the fault is high, then we want to trip the breaker fast. So the higher the current, okay, the less time it takes to trip. If it's a low current, then it takes more time to trip because we're basically hoping that fuses are going to take place. But there are a couple of boundary conditions, and let me point that out. When we have this boundary condition over here, there is a minimum current that there has to be there before a relay would even consider starting to trip a breaker. Okay? This would be the normal operating range. This is the current that would be normal. So normal load on the system would be operating down here below the set point of the relay. If the relay sees current greater than that through its CTs connecting to the breaker, then it says, okay, I'm going to trip. But any current in this point is going to take a little bit more time to trip than you go out here. And at this point, if the current is greater than this set point here, then we're going to talk about an instantaneous trip. That gets to a point where fast trip, the fast tripping occurs. If we have a short circuit right out of a substation, we want to trip in as little a time as we can. That's high energy. But if there's a high resistance fault causing a lower than maximum fault current, but greater than normal current, then we're going to trip in some kind of a delay. And that's basically part of coordination. And when you see this little drawing up here, electromechanical, it's saying that we got a spring down at the bottom. If I can create enough magnetic field from my CT current, I create enough magnetic field to move that disc around against the tension we put on that spring, then it's going to make those contacts connect, and that'll trip the breaker. So electromechanical deals with discs and coils, the older type relays. The solid state relay says, all right, if I get a CT that's going to give me that current, trip. You know, and my normal operating range is thus. So that's a difference between the solid state. And the solid state is so much smaller, so much compact, so much easier. Plus you can have communication schemes where you can dial into the relay and check history. It records before the fault, after the fault. You get a snapshot of what actually went on in all three phases and all three currents, the voltages. Very informative type, relay when we deal with the solid state. That's why there's so many more solid state relays now than in the past, replacing the electromechanical relays. Okay, let's talk a little bit about protection on distribution. On distribution, it's very basic. We're talking about a radial scheme. Normally, it's a radial. So a feeder has one source, and then it just goes out on the highways or underground, and then there's fused laterals coming off of the main feeder. Okay, typically there are no fuses on the main feeder, just fuses going off on laterals. Until you get to the very end, then that might be a fused lateral in itself. Okay, so we look for ground overcurrent. If a line falls on the ground, we get ground current or an imbalance on the three phases significant enough to represent a ground fault, then we're talking about tripping the distribution feeder. If there's overcurrent on the phase, it could be a phase overcurrent condition. Let's say a tree branch went across two phases. There could be abnormal phase overcurrent conditions. That would trip. There's automatic reclosing on distribution mainly because of lightning and taking the lightning strike and the lightning arrestor short-circuiting the distribution, which causes the breaker to trip, and then you automatically reclose. Then the load shed, the automatic under-frequency load shed. If our system frequency drops below a certain frequency, it's the load that gets tripped. Because if we have excess generation, then we have a high frequency. If we have undergeneration, let's say we trip the generating unit or a transmission line that's a source line, then we end up with low generation and more load than we have generation, and that's going to slow our frequency. So if we have a low frequency condition, it's probably because we tripped a generator or source line, so now we're going to end up shedding load in order to maintain that balance. So automatic under frequency load shedding is typically done on distribution. Here is the curve that represents an under frequency load shed relay. Just to give you an idea here, when you see this curve, you have set points and you have frequency. Now notice you have frequency of 60 hertz up here and 57 down here, but we're talking about frequencies right around 59, a little bit high, the high 58s where we're actually load shedding. And when you look over here on the right side, it says that generally we'll trip 10% load at 59.3 hertz. Now 10% of load, that could be several feeders in the system or in that area. If the frequency drops, then that relay is going to, on this breaker, if it's set for 59.3 and the frequency drops, that breaker is going to trip. And then you want to shed another 10% at 59.0. So there might be, you know, the relays are set for 59.3, 59.0, and 58.7. We're going to trip another 10% of our load. So if our frequency drops to somewhere around 58.7 hertz, we're going to essentially automatically, quickly shed 30% of our load. So we're trying very rapidly to correct an imbalance between load and generation. So that's what under-frequency load shedding is all about. It's a tricky situation to really get a good handle on, but it happens fast, and it happens faster than system control operators, even though they have the ability to shed load themselves. By the time you say open that breaker and you go through a command and a confirmation and then an action, when you're talking about something like 2-second scans it takes to go through all the RTUs out there through the SCADA system, it's about refreshes every 2 seconds. So you could take 2 seconds, 6 seconds or something like that if you know what you're doing and which breakers to trip, or if you have automatic schemes that say I'm going to trip 10% now, these can be much faster. So a lot of times you'll get alarms that these breakers tripped and it's on under frequency. Well, that's a reaction based on system protection. Okay, now let's talk a little bit about what kind of protection schemes you find on transmission systems. Completely different. Most of the time the transmission lines are not radially fed. There are radial transmission lines serving a substation somewhere out in a rural area. But generally speaking, this transmission system protection is designed to have multiple transmission lines networked together so that at a substation you could have sources and loads on transmission line depending on which way the power flow is going, whether it's real or reactive power, a lot of conditions. So normally the transmission system is set up on zones of protection, and these zones of protection overlap each other so you have backup coverage. So let's look at this. This particular drawing shows several red circuit breakers that are closed, and this will match up on your simulator. You'll see red circuit breakers that are closed, okay? And there's transformers and there's generators, and then there's one breaker there on the bottom that's green, and that shows open. So here, let's look at this particular scheme. These lines right here could represent, you know, lines that are 50 miles, 100 miles, what have you, and these are substations, okay? So we have substations and transmission lines. So let's look at what type of protection schemes we might find protecting transmission. First of all, let's talk about the generator. Generators have zones of protection where there's, you know, breakers, circuit breakers. If there's a problem with the generator, many different things. It could be a field to ground short. You know, the field is in the center on a rotor, but if there's current going from the rotor to ground, obviously there's a problem there. Or maybe there's overvoltage, or maybe there happens to be excessive frequency, like perhaps the load was removed out in the system and now frequency is too high, so it will trip on overspeed. Or maybe motoring a generator is going to trip. There's many different reasons you would trip a generator. And if you do, there could be a problem. There could be a problem with electrical wiring anywhere in here, so we're talking about tripping for generation. Now let's talk about line protection. On a transmission line, we're protecting this particular line using these two circuit breakers. Now, when we're setting up protective relay schemes, we're using the CTs on the opposite sides of the breaker. That provides overlap. For example, we're looking at CTs on the bus side of the line, the bus side of that breaker for protecting that line. And the reason for that is there's multiple. If that breaker doesn't trip the line, the current in the CT doesn't go to zero. See, so then if the current in the CT on that breaker doesn't go to zero when that breaker is supposed to trip, that means there could be a breaker failure condition. The breaker itself failed, okay? And if that's the case, then if the current in that CT doesn't drop to zero in a predetermined time, then all the breakers associated with keeping that breaker energized is tripped. So in a case like this, if that breaker does not trip, then we have to trip that breaker, and remotely this breaker, which might involve telecommunications systems in order to tell the other breaker to trip. That current has to get to zero or it's a breaker failure. So we use the CTs on the opposite sides in order to protect that line, because it also includes protecting the breaker. Okay, now when we talk about transformer protection, it's usually differential protection. Now the power going in must equal the power coming out. Okay, and if not, there's a problem internally, like a short circuit in the transformer, and that energy is going to the grounded transformer, maybe the case is grounded, what have you, so the power coming in is going to earth and returning back to the source, and it's not all coming out the secondary. Or there's a problem on the outside. Maybe a bird or some animal got into the bushings up on the top, and the power going into the transformer, some of it is going through the animal or what have you into the earth, and it's not coming out the output secondary. So we have a transformer differential condition. Okay, now we again use the CTs on the opposite sides of the breaker to make sure that when we trip for a transformer differential, that the breakers themselves actually tripped and the currents went to zero. Then we know we've isolated the problem. So that's a type of transformer protection. Okay, the next one to talk about is bus protection. So looking at this bus right here, the current going into the bus must equal the current coming out. If not, there's a bus differential issue. So we have protective relays that are looking at bus differential. If the current going into the bus doesn't equal the current going out, then there could be an animal or something in the bus causing power to go to the ground grid, and therefore that's energized all the breakers that could keep the bus energized. Okay? So bus differential can trip several breakers just to get that bus de-energized. Okay, that's bus differential. Okay, when you put it all together and you look at an overview here, bus differential is overlapping generator protection, which is overlapping transformer differential protection, which this bus is overlapping the differential protection of the transformer, and it's overlapping the line protection. So we use CTs on the opposite side to give overlapping protection, and that's basically how transmission is set up in a substation. The transmission lines themselves could have zone relaying and zone protection, looking at different faults at different distances out on a line, but we're talking about overall, what you understand, that is the protective relays, the CTs, the PTs, and the associated equipment that is operating the protection scheme throughout the entire electric power grid. Okay, another important aspect of system protection is synchronization. Now, when a generator is to come online, it must match the system before you can actually close the synchronizing breaker. Sometimes you have what's called a sync check relay. When you're synchronizing, we'll go through the steps here to point out how important it is and what you have to do in order to close that breaker. And some of these points are so important that if you tried closing the breaker without protective relaying blocking you from closing, then you could have catastrophic failure and literally destroy a generator. So protective relays protect the operator and the system for closing into a system out of phase, for example. So let's look at what are the conditions. And there are basically 4 conditions. One of the 4 is satisfied right during construction. And what we have to match is we want to make sure that before we close this synchronizing breaker, that this generator and this system are in sync with same frequency. The generator's got to be running at 60 cycles per second, so as the system. We have to make sure that we operate the same voltage on both sides, that we have the voltage of the output of the generator to be very close and matching the system voltage. So on this synchronizing breaker, we're going to have CTs and PTs on both sides. So we're going to use the CTs for matching frequency, we're going to use the PTs for matching voltages, and then they have to have the same phase angle, which means if the system is starting the positive side of a cycle, we want the generator to also be starting the positive side of the cycle. Even though it might be running at 60 hertz, we don't want the generator to be at the negative side of the cycle when the system is at the positive side. That's 180 degrees out of phase. That would be like having 2 locomotive engines crashing into each other. I mean, there's magnificent energy that we're talking about here. So we want to make sure that the trains are both going in the same direction, and we just want to put them together, connect up, and be moving on. So we want to make sure we match phase. So a sync check relay says, okay, we have a little leeway there. Maybe within 12 degrees, as long as it's within 12 degrees, we can close the breaker. So there's a permissive system that says when we get the phase angle and the frequency to be within 12 degrees, then when you push the breaker close button, it will close. Otherwise, you could push it all day long, and the protective relay is not going to allow that breaker to close. So when you have the right phase angle, the right voltage, the right frequency, you're pretty much ready to close, but we also want to make sure we have the same rotation. That means that the rotation on a system, it might be red, blue, green, red, blue, green. We want to make sure the system and the generator both have the same rotation, red, blue, green, red, blue, green, 1, 2, 3. Or maybe it's 3, 2, 1 and 3, 2, 1. Whatever the rotation is, they've got to match. And that's something that gets taken care of during construction. When you're putting the taps on the lines, even though they're all aluminum, you want to make sure you got the right phase rotation. Once you have that and built, otherwise you change the jumpers around to make it work. Once you have the same rotation, that stays forever. You don't have to change that. So the operator is really looking at just the first 3. So we want to match frequency, match voltage, and match phase angle. Then you can close the breaker. Okay, so that's the basic parameters behind synchronizing a generator. You can't just take an emergency generator that you have in your building and just close the breaker, because those first 3 things could all be off. All right, you could have some major problems. So you have to have a synchronizing scheme. Now here is a synchronizing scheme. This is a synchroscope. And what happens here is you can actually, close the breaker and let the synchronizing relay actually do all the work, to match the voltage, match the frequency, match the phase angle, and close. And what we're trying to do is get it close. And what happens with this needle is this needle is going around between the system and the generator. If the generator is running a little too fast, then this needle is going to be going like this. If it's running too slow, then the needle is going to be going this way. So you're going to increase the amount of steam to the turbine, for example, to increase the speed of the generator so that it's coming up like this slowly, and then when you get right up to the point there, then you close the breaker and it locks in. Okay? In the old days, we used to do it with lights. You used to have lights the system and the generator, okay? And when you got them close, we're blinking together, we can close. A little bit crude, but that's the way it was. Nowadays, we can really lock into a nice clean sync, and when that generator kicks in, you hardly even know it. The transient on the voltage is minimized. Those are the kinds of things. This is just an overview of system protection, just enough to kind of give you an idea what system protection is all about. There are courses just on system protection. You can make a career out of just system protection. It's very, very sophisticated and very interesting if that's the kind of work you like to do. Okay, let's summarize what we just learned in the module on system protection. Okay, first, we explained how system protection is different than personal protection. Personal protection, remember the rubber goods and those types of things we're going to talk about later in safety. We talked about the fundamentals of solid state versus electromechanical protective relays. Electromechanical are the older types that have magnetic fields and coils and springs. The solid state is more of the electronic type. Then we have we talked about the various relay schemes in use today. We're talking about differential bus, differential transformer, line protection, generator protection, overlapping zones. All of the protective relays are operating off of the CTs and PTs in the system to give us system protection. We described how to synchronize a generator onto the power grid. Remember the synchro scope. Want to make sure all the phase angle between the two systems is within acceptable region before the relay allows you to even close the breaker. So these are the different areas in system protection that very big, very high level overview, but it gives you an idea how to clear faults automatically or under frequency load shed and over current conditions, those types of things. This is how system protection is set up on a power system.